Earth is in a long-term cooling phase of its orbit around the Sun. So why is it heating? A simple answer follows. Have a carbonated soda as you watch the video.
This is our climate. What do I mean? Most of us have heard of the ice ages from movies.
Everybody down!
20,000 years ago, places like New York City were covered in ice. But that wasn't the only time. There were a bunch of ice ages, going back millions of years. And here's the crazy part. By looking at cores of mud from the bottom of the ocean, we can tell that these ice ages actually came and went on a schedule, like clockwork. In fact, the entire world got hotter and colder with the ice ages. So what caused these huge swings in Earth's climate? Actually, it was clockwork, corresponding to slight shifts in Earth's orbit, now called Milankovich cycles after the Serbian scientist who started to figure this out. We know that the gravitational pull of the Sun, Moon, and other planets makes the Earth's axis wobble like a top on a cycle of about 20,000 years. The tilt of the Earth also shifts about every 40,000 years. And the shape of Earth's orbit around the Sun goes from more circular to more like an oval on a schedule of about 100,000 years. All of these changes affect how heat from the Sun warms the northern hemisphere where ice sheets can grow. So, the same types of planetary movements that create our days, weeks, and years actually seem to also create something like superseasons, our climate. But that's only part of the story. Because with the orbital cycles, when the northern hemisphere warms, the whole planet warms. And when the northern hemisphere cools, the whole planet cools. Changes in Earth's position set the tempo of the climate clock, but they don't explain why the shifts in temperature are so extreme and why they're global. Going from times when New York City could be covered in a thick layer of ice to times like today, when it hits 100+ in summer. So what else is going on here? A major clue came when scientists extracted cores of ice from Antarctica, dating back hundreds of thousands of years. And inside of them were trapped little air bubbles of ancient atmosphere. They revealed the amounts of carbon dioxide in the atmosphere going back 800,000 years. Remarkably, the rhythm of this record matches that of the ice cores recorded in the ocean muds, almost perfectly. We know that CO2 is a greenhouse gas, a gas that traps heat on the planet. So this could explain those huge global shifts. But where did the CO2 come from? Why would gas in our atmosphere match the tilt and wobble of Earth? This is where that can of soda comes in. These are carbon dioxide bubbles, now visible because I just depressurized the can of soda. One theory is that as the ice sheets melt, they release pressure on the world's volcanoes, setting them off like a freshly opened can of soda. But that can only account a little bit for what was going on. Another theory is that the oceans act like a sea of soda. How do I get a ton of bubbles to come out? By stirring it up. The same thing happens with the world's oceans. They also contain carbon dioxide. And our planet, the blue marble, is 70% ocean. Now, even though a can of seawater doesn't have quite as much carbon dioxide as a can of soda, that's still a lot of carbon dioxide in all of the world's oceans. And when ice sheets start to grow, that changes everything. The wind patterns change, which shifts ocean currents, and that changes how the ocean mixes. Scientists believe that the biggest reason CO2 tracks the orbital cycles is because when the planet warmed just a touch, that enhanced ocean mixing. And then just like our stirred soda, the oceans lost some of their fizz to the atmosphere. And more CO2 in the atmosphere meant more heat trapped on the planet. But today there's another source of carbon dioxide. Every year, humans dump over 30 billion tons of carbon dioxide into the atmosphere. That's well over 50 times the amount that comes from volcanoes. As a result, We're warming the planet 10 times faster than anything we've ever seen before. The tight link between the orbital cycles and the atmosphere is gone. We've actually broken the climate clock.